let's see how given an arbitrary symmetric or Hermitian form, how to get an orthogonal basis. Okay. So this is the first theorem. Let V be a real, okay, wait a minute. Let's start with the form instead of a vector space. Okay. Let this be a symmetric form on a real vector space V, or a Hermitian form on a complex vector space V. Okay. So then there exists an orthogonal basis of V with respect to the given form. Okay. So let's begin with the proof right away. So suppose the form is identically 0, then the claim holds trivially, right? Why? Yeah. Because you just, somebody told it. Exactly. So in particular, if you take the basis elements, they are outputting 0, right? So any basis is an orthogonal basis if the form is identically 0. Okay. The claim is trivial if the form is identically 0. As any basis is orthogonal. Okay. Is that point clear to all of you? Because if it is identically 0, you put any two vectors, you are just getting 0 as an output, right? So in particular, for that's true for all the basis vectors. So that means the basis is orthogonal. Okay. Now, if the form is not identically 0, then it is the case that you have seen in one of the exercise sessions earlier. Okay. If the form is not identically 0, then there exists some V1 in V, such that V1 is not equal to 0. That was an exercise in one of the tests, right? How did you do this? Yeah, by contradiction, of course. I mean, well, for symmetric it is rather simple. So you just take a pair of vectors, and so this is just a small recollection of the proof of this claim. Okay, proof of this subclaim. This subclaim means this one. Okay, that is, if for all, if the form is not identically 0, and if this is equal to 0 for all V and W, in particular, well, if it is not identically 0, then that implies there exists V and W such that VW is not equal to 0, right? If it is not identically 0, at least for a pair of vectors it is not equal to 0. Now if VV, I mean put V here, if it is non-zero you are done. If WW is non-zero you are done. Suppose neither of that is true, then so if neither VV nor WW is non-zero, then at least one among V plus W or V plus IW is non-zero. Okay. You don't even have to think about this if the if the vector space is real. So then V plus W would give you 2 V comma W. Okay. And V comma W is non-zero, and of course this is not a, it's just real, it's not a field of characteristic 2. So that means V comma, this would be not equal to 0, because this would be just equal to 2 VW if both this and this is equal to 0. Okay. And both of these are, if these are equal to 0, then you get this to be equal to non-zero for the symmetric case. In the Hermitian case, this will give you the real part of V comma W, and this will give you the imaginary part of V comma W. Now if V comma W is not equal to 0, then either the real part or the imaginary part is non-zero. Okay. Actually twice the real part and twice the imaginary part. Yes, please. No, it's not. So that's what I was meaning. I said that if for the real case, don't even look at this one. Just this one would suffice. Okay. Otherwise, you have this or this. At least one of these should be non-zero. Okay. Is non-zero. So in any case, you are getting a vector whose product with itself is not equal to 0. Okay. Well, we are not calling it an inner product yet because this is not given to be positive definite. We are just calling it a symmetric bilinear form or a Hermitian form. Okay. All right. Now that in particular means that not only in the trivial case, but we are also done in another case. Which case? You got one vector such that this is not equal to 0. Take that to be your basis for the dimension 1 case. Please come in. So if dimension V is equal to 1, then then we are also done. Then let V1 be the basis, just okay. All right. Now, so we are done for this case, dimension V equal to 1. Okay. And actually, here it doesn't matter whether this one is 0 or not, because you are not taking product with other vectors. Okay. Okay. But actually, this. So what I want to say is that, this choice will help us also in the induction step. We are going to now proceed with induction. Okay. So what we are going to do is, yeah.
How are we done for dimension V equal to 1?
Well, for dimension V equal to 1, you just have to take one element which is not equal to 0, right? So if you take any basis element, in particular, this will ensure that V1 is not equal to 0. Okay, because if this is not equal to 0, then V1 cannot be 0, because if you put 0, 0 there, it is. Yes. What is the definition of an orthogonal basis?
If you take two different,
exactly. Yeah. Okay. So now let's assume that the claim holds for dimension V, and for V with such that for all V with dimension V equal to n. Okay. Now let's assume. Now let's consider. Okay. Let's consider the case where dimension V is equal to n plus 1. Okay. Still, we can choose a vector such that v1 is not equal to 0. Right? So, choose a vector v1 in V such that this is not equal to 0. Let that be the first element in our basis. Okay. So, and let W be defined as the span of V1. Okay. Then what can you say about the form on W? Is it degenerate or non-degenerate? It's a symmetric form or a Hermitian form that is given to you. Okay. Now you have this form on W. Okay. What can you tell about the degeneracy or non-degeneracy of the form on W? Because exactly, its gram matrix is non-singular. It's just this one. Okay, 1 cross 1 gram matrix. Okay. So that means in particular, if we apply the theorem that we have proved in the morning, V decomposes at W direct sum W perp. Okay. So in particular, the form is non-degenerate on W, since the gram matrix is non-singular. Okay. Or you can say it directly, because it's a span. Okay, span of a single, V1, this vector V1, and then, if it is not self-orthogonal, that means in particular the null space is 0, right? Okay. So that will let us, right? Can I wipe this theorem? Is it fine? Okay, thank you. So then V decomposes as W direct sum W perp as the form is non-degenerate on W. Okay. So now look at the induction hypothesis. What was that? That the claim holds for all V with dimension V equal to n. So in particular, it holds for W perp. Okay. So now by the induction hypothesis, the claim holds for W perp as the dimension of this is n, right? Let V2 dot dot Vn be an V2 dot dot Vn plus 1 it would be, sorry, be an orthogonal basis of W perp. Okay. So we'll just put V1 there, okay, to construct the basis of V. Okay. Then B equal to be defined by V1 V2 dot 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 Vn plus 1 is an orthogonal basis of V. Okay. All right. So there's the proof. Okay. Does it construct an orthogonal basis given any symmetric form on a real vector space or a Hermitian form on a complex vector space? Okay. Now which part? This one. Now why are we interested in constructing an orthogonal basis? Because that would let us write down the orthogonal projection that we have seen earlier explicitly in terms of this. Okay. So here's the theorem. Let, okay, the assumptions as before. Okay, so let this be a symmetric form on a real vector space or a Hermitian form on a complex vector space and let W be a subspace of V such that the form is non-degenerate on W. Okay. Let W1 dot 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 WR be an orthogonal basis of W. Okay. So it's a symmetric form or a Hermitian form, okay, on a real or in a complex vector space. I mean, a symmetric form on a real vector space or a Hermitian form on a complex vector space, and we're taking a subspace of this W such that the form is non-degenerate on this. Okay. Now we already proved that for any vector space, if you are given a symmetric or a Hermitian form on that, there exists an orthogonal basis. So in particular, if you restrict the form on W, you also get an orthogonal basis for W. Let this be such a basis. Okay. Then we are going to write down the formula for orthogonal projection. So do you recall what was that? Right. Yes. So once it is non-degenerate, or once W, I mean the form is non-degenerate on W, we have always such a decomposition. Okay. And then we can write every element here V as W plus some V prime. This is the orthogonal projection of V in W. Okay. And we were denoting it by PW or pi W. Okay. Okay. So let's write down the formula for that. So pi W, okay, wait a minute, this is an orthogonal basis. Then the orthogonal projection pi W from V to W is defined by pi W V equal to summation I running from 1 to R Wi comma V by Wi Wi and Wi. Okay. Wi Wi. So what's the first question here? Once we write down this formula, exactly why this is not equal to 0 for all i's. It's non-degenerate. Okay, it's given to you that the form is non-degenerate. Okay, during the construction, we haven't assumed that the form is non-degenerate. We just assume that it is a symmetric form, okay, or a Hermitian form. And then if it is not, if it is identically 0, we have by default an orthogonal basis. And if it is, if it is not identically 0, then there would be PW for which it is, their product is not equal to 0. That would give us a vector such that V1 is not equal to 0. So that was our first step, and actually that also helped us to go from the step with dimension V equal to n to dimension V equal to n plus 1. Okay. But here we are in a easier case because we are assuming the form is non-degenerate. Okay. So in particular, that means that you cannot, there is no vector which is orthogonal to all of them. Or you can also think of all of the vectors in W. There is no vector in W which is orthogonal to all of, except 0 of course, which are orthogonal to all of this. Now if Wi is 0 for some I, that would mean that it is, yes, it is perpendicular to all the basis vectors. So therefore it is perpendicular to all the vectors on W. Or you can also think of this in terms of the Gram matrix, because since it is non-degenerate and since it's an orthogonal basis, how should the Gram matrix look like for an orthogonal basis? Diagonal. And since it's non-degenerate, the determinant should be non-zero. Exactly. So all the diagonal elements should be non-zero. So this should not be 0. Okay. So therefore, this sum indeed makes sense. Okay. Then okay. So this is the orthogonal projection, and let's write it down somewhere. Then the proof. Well, there is not much to prove here because we see by definition this goes into W. Okay. This is just a scalar. Okay. You are multiplying with, so this is just a coefficient of this Wi, and Wi's are the basis vectors. So this summation is indeed mapping V into W. Okay. So all you have to show is that if you subtract this one from V, that is perpendicular to W. Yeah, any doubts, Sanskar? Okay. Okay. Okay, and this last step, that is, okay, so here is the proof. Clearly, well, we shouldn't start anything with clearly, excuse me, okay, because otherwise you can write the and answer your exam papers as clearly the claim is true. Okay, no more for that. So we should write, okay, since pi w v is a linear combination of the basis vectors of W, hence, okay, we don't need to write that anymore because this is a linear combination of the basis vectors of W. So we get, so pi W V is indeed in W, pi capital W V. Okay. So it suffices to show that V minus pi W V is in W perp, and the proof is exactly as something that we have done before. Okay. How are we going to show this? With what? Exactly. We take the inner product with, not inner product, the form. Here we are not given the form to be inner product, but we can put in the arguments this wi's, and in the other one v minus pi w v. Okay. And it suffices to show then, well, suffices to show that wi v minus pi w v is equal to 0 for all I. Okay. And what is this? This is equal to, and this is if and only if wi v minus wi pi w v, okay, by bilinearity, and that should be equal to 0 for all I. So what we are trying to show, that wi and pi w v, if you take the product, you get this as an output. Okay. All right, and that should be clear from this formula. Let's write it down anyway. There's a movie called Deja Vu. Have you seen the thing? That one of the, I mean, previously it has been directed by one of, I mean, two of your alumnus. Okay. And do you know what exactly deja vu means? What? What? No, you have seen something earlier. Okay. Exactly. So how we are going to do this is something that you have seen earlier. Okay. Okay. So this is indeed a deja vu. Okay. Pi w v. Okay, let's compute this. Okay. So wi sum small wi and wi, I running from 1 to r. Okay. All right. What happens now? This is a sum, and it's linear in the second variable, right? Oh, okay. Maybe we write j here, right? Because this is wi and that is also the diamond variable is the same. So j running from 1 to r, wj vi, and yeah. So which one among these survives? Yes, only I, Wi, right? And if you take the product there, that cancels with this one, right? So you're left with Wi V, which we should have. Okay. So indeed, we have that this is equal to 0. Okay. So Wi comma V minus pi W V, this is equal to 0. So मैं ये बोल रहा था कि you have seen this earlier, just that. All right. So where do we see this earlier? Here. I hope this is you have written this down. Okay. So we saw that if you take some vector space V, some vector in that, and some subspace W, then okay, we can project it on W. This is V, this is pi W V, and this one is V minus pi W V. Okay, and these two are perpendicular to each other. Okay. Yeah. So when we drew this picture, what we did earlier, at that time we assumed that we have an inner product. Here we didn't. Okay. We just assumed that the form is non-degenerate on W. Okay. That gave us an orthogonal basis with respect to which we defined the orthogonal projection. Earlier what we did, we just took the product of V with the elements of the orthonormal basis. Okay, just a small notation. O in B, we will use this to as a shorthand for orthonormal basis. Okay. So in particular, when this was an O in B, this would have been all at once, right? So this is just Wi comma V times Wi. Okay. All right. Now we are very close to Gram-Schmidt process. To finish. Yeah. Which one? This part? Okay. Note that this is a linear combination of these Wj's. Okay. And remember also that W1 to WR, this is an orthogonal basis. Okay. So now, since this is a linear combination and since the form is linear in the second component, you can expand this. And once we expand this, in each of the things you will get Wi times some constant times Wj. Okay, that constant you can take out, and inside you will have Wi comma Wj. Now Wi comma Wj will be 0 unless I is equal to j. Okay. So only that thing survives. Everything else is killed by the inner the form with Wi, the output of the form with Wi. Okay, so only the case when j is equal to I, that stands out. Everything else is 0. Okay. Now when j is equal to I, this one is Wi, and this one is also Wi. You are taking the inner product with Wi here, so Wi here. That gets cancelled with this one. Here you just have Wi comma V, which is out there. Okay. And now we are having that this is equal to this. Okay. So here I just have plug these two together. This is equal to this means that if you take it on the other side, you get V minus pi WV.
So it's Wi, not
It is Wi, of course. Yes.
Are we using this formula to prove that it is an orthogonal projection?
No, we already have shown that if the form is non-degenerate on W, so let's recall from today morning, okay? If this is non-degenerate on W, then you can write V as a direct sum of W and W perp. Okay. So once you have this decomposition, that means every vector in V you can write as a unique sum of an element in W and an element in W perpendicular. So in such a decomposition, suppose you can write some vector V in V as some W plus V dash in, so W in W and this one in W perp. Okay. So this W is then the orthogonal projection of V in W. Okay. So that W is corresponding to this one by WV. Okay. And V minus by WV is just this one, V dash. Okay. Okay, we are going to talk about the Gram-Schmidt process. Actually, it's better to write it down here because the picture explains it nicely. Okay. Gram-Schmidt orthonormalization procedure. Okay. So this is just an algorithm. What it does, given a vector space V with actually not just a vector space, an inner product space, that is a vector space with an inner product on this. Okay. Inner product this on V and a basis B, say V1 dot 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 Vn of V, an arbitrary basis. This procedure outputs an O in B, say B dash equal to W1 dot 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 Wn. Okay. So before we show you exactly what it does, I mean this or the previous formula that we've written down is basically what we are doing. Okay. But let's explain it first with the picture. Okay. So you are given such a basis, an arbitrary basis, and then you would get out of it an orthonormal basis. What you will do, at first you will just normalize the first vector V1, you will just normalize it. Okay. Then you will take the span of that, okay. Project V onto that, okay. And then you will get a decomposition of V. I mean you can project it on the span of the that V1 or on W1, I mean on the span of W1, and there would be an orthogonal complement. I mean this is a projection in the orthogonal complement, right? So you will now forget about this. Okay, this is already in the span of the previous vectors. Okay, and consider this as your new vector. Normalize this again, okay, and proceed. So then in the next step, you will take all the basis vectors in this space W, include this one as well, and take the span of that. Okay, that's your new space W. Now take the next element in your basis, project it on W again, okay, and get the orthogonal complement which is perpendicular to this. Okay, orthogonal complement. I mean, take the component of V which is perpendicular to this plane W. Okay. That's again your new element. Normalize it and proceed. Okay. I'm going to write down this soon, what we are doing. Yeah, it's very simple. So, yeah. Okay. So let's see. Now, you are given this basis v1 to vn, okay, and then you are defining w1 as v1 by norm of v1. Why can we write this norm? It's a positive definite thing. Okay. So then take w1 as the span of w1. Okay. w2 you are going to define as pi w1 perp of v2 divided by norm of pi w1 perp v2. So you are taking the projection of v2 on w1 perp and then normalizing it. Yes.
What is
Perpendicular, orthogonal complement of w.
also called normal?
It's not a normal. It's the difference on.
Isn't called orthogonal? Instead of calling it part sounds very funny.
Okay. Yeah, but orthogonal is a longer word. Anyway, if you, yeah. So, by the way, this one is of course a normal to it. Understand the difference. So this is normal to this space. Okay, but this is not the only thing. There.
Normalize it also.
No, it's not only normalizing this. W perp or W, I mean orthogonal complement. Actually, perp is the name of this sign. If you type it in LaTeX. Okay. So in LaTeX, how do you type it? Okay. You write W. Yes. Okay. Perp for perpendicular. Okay. Okay. So by the way, what I was saying is that this is not the normal. I want to understand the difference. So this is not just this one vector. W perp is the set of all the vectors which are perpendicular to W. Okay. So it's the set of all such vectors, not a single normal. Okay. What? It will form a whole circle? No, it's actually the set of all such. Well, you can think of this as a, I mean, if you want to see it visually, is a set of all the parallel lines parallel to this. Okay. At least in this picture, what we have written down, it's not a circle. Okay. Now, how should we define W2? W2, capital W2. Exactly. Span of W1 and W2. Okay. And then, how should we define small W3? We'll visualize this in a moment. But I mean, if we just induct on this, how are we going to define W3? Yes? Pi of W2, just pi of W2? Pi, yeah. Of V3 now, okay? And then we normalize it again. Normalize pi W2 perp V3, okay? And we define again W3 is equal to the span of W1, W2, W3, and so on. We continue till the end. Bishesh, yeah.
Is W3 perpendicular to W?
W3 perpendicular to? Yeah, now you tell me. Forget about the normalizing factor. Just look at this. And this is just a scalar, right? So you are asking whether that this thing pi w perp v3 is it perpendicular to w1. Okay. Now, I mean pi w perp, that means that you are projecting v3 on w2 perp. What is w2? We defined it somewhere here. It is span of w1 and w2. Okay. Okay. So these are the spaces which are spans of. I mean, you are taking one vector first, taking the span of that. Okay. Projecting w2 to the, I mean, to its orthogonal complement. Okay, and normalizing it. Then you are defining the new space, which is the span of these two vectors. Okay, and projecting the next vector in the given basis to the orthogonal complement of this, normalizing it again. Okay, Vishesh. So that's the idea. Okay. Yeah. You tell me, is it possible? What happens if w3 is 0 or that small w3 you mean? Well, can it be 0? I mean, that's of course a valid question, but can it be 0? What it means? If w3 is equal to 0, that means this projection is equal to 0. That means what? V3 is in w2. Exactly. So v1, v2, v3 are linearly independent. And this one, this w1, w2 is exactly in the span of v1 and v2. You see? We defined it in that manner. Okay. All right. So let's continue. Vishesh, so did you get the intuition yet? I mean, what we are doing? Not yet. So suppose, I mean, at each step we are just basically using this picture in every step. Okay. So in the first step, w is the, well, at least the first step should be clear, right? You are normalizing the first vector. Isn't that clear? I mean, what we are doing? The norm of any vector is given because it's an inner product. We defined norm v as this, right? And we can do that because it's a positive definite inner product. So, well, of course, for all v not equal to 0. Okay. And then, well, even for 0, it's just 0 then. Okay. This is an unnecessary condition. Okay. Now, what you are doing here, v1, you are dividing v1 with its length. So you are normalizing it. That means the length of w1 is just 1. Okay, and then you are taking the span of this. Okay, well, of course, this span is equal to the span of v1 because it is nothing but a scalar adjustment. Okay, normalization. Okay. Now, what you are doing, you are exactly in this picture. Now your w is the span of the first vector. Okay. What you are doing, you are projecting v on the span. V is, well, the next element in your basis. So v2, exactly. Okay. So what you are doing, you are taking v2 and projecting it on the space which is perpendicular to w. Perpendicular to w1. No, well, yeah, capital W1, exactly. But well, this picture we are using it several times, and that's why we are not writing w1 here. Of course, I mean, in the second step, this is v2, this is w1, this is pi w1 v2, and this is what? v2 minus pi w1 v2. Okay. Yes. It is. What is the definition of perp? Yes. What? Please, Nitesh. What? Small w1. Yes. This is, you are just normalizing this. So you are taking the first element of the basis, you are normalizing it to v1. That you understood? Okay. Then w1. It's a dimension 1 space, right? Well, you are taking a vector, and so we are taking a vector W1. What is the span of this? It is the entire line. Okay, that's it. So W1 is that, and then you are taking your vector. So this is what V2. Then you are projecting it on W1. Okay, and then you are taking its orthogonal complement. Okay, so this would be your the next thing, that perpendicular, right? And then you are normalizing it. Okay, so you are taking the unit vector along this direction. Okay. Yes, we are continuing to do so till we are getting the nth vector in our. Yes, Vishesh. You understood the entire thing? Okay. Now, Ayon, since you didn't leave the class, I hope you are with the class now again. So, could you please tell me what do we mean by pi w n perp? No. Wait, it's we are saying pi w n. Wait a minute. So suppose we are just considering. So what should be the last step of this? Of course, in the same manner, you can continue, and at the end, you will have Wn as pi Wn perp Vn by, sorry, not Vn. This n minus 1, right? And here it will be Vn, right? These are the same indices, right? Okay. And here you will have pi Wn minus 1 perp Vn. Okay. Wn minus 1 perp. Yes. Well, yeah. But actually well, yeah, at first Wn perp, yes.
Yeah, that is like it's a positive definite. Please, the form is positive definite of V.
Right.
So because of that, like the Wn, the space Wn is V itself.
Right.
So Wn perp will be V perp, but
Yes.
V perp is V.
0. Okay. So Wn perp would be in particular 0. Okay. But on what do we mean even by this one? No, not this one. Wait a minute. Pi Wn minus 1 perp Vn. We defined only the projection of this onto this, but we have not defined what is this, did we? So how we are going to write this? Because we are given a basis b equal to v1 to vn, okay, and we are forming b dash equal to w1 dot w. Well, before we have defined this, we just have this up to wn minus 1. We have not yet defined what is wn, because we are defining wn in this manner. Okay, so we want to write this in terms of this basis, okay, up to this one. Okay, b dash is not that, of course. B dash is a little more, but this is something which is relevant here to express this. Now, how are you going to express this in terms of w1 to wn minus 1? Try. Make an effort. Sigma of k running from 1 to n, 1 to n. Wk comma k vj, and And what is this V?
from that.
Vj, this one. But we are defining the map on Vn. Okay, so forget about this Vn. Maybe that is your V. That's perfect. But what should come here?
In these times,
V? But it's, if you write V here, you see these are all scalar multiples of V. So that means you are taking just a sum of elements on a line. It will fall again on the line. There is no linear independence. For a basis, we
V minus this sum.
V minus this sum, it's still on the line, the span of V. So this should not be V. What is the other option?
Vn minus 1.
Vn minus 1? Close, but not, this is not Vn. Not Vk minus 1. Okay, do you recall, if we have an orthonormal basis of V, how do we, so suppose B dash, you know it full, okay? Suppose W1 to Wn is a full orthonormal basis of your vector space. And you are given some V in V, okay? Given the information that this is an orthonormal basis, how do we express V in terms of this? Do you recall that?
V1, V1 W1 plus components.
What again?
If the components of V are V1, V2,
V. If the components are
and V1, V2 dot Vn, then the vector will be
what do you mean by the components? The projections on the spans or what?
projections of V.
Okay. So what is the projection of V on, so what is the projection of V on W1?
V1, comma W1.
V1, here you are just given V. So
V, comma W
V comma W,
by W, comma W.
V comma W by W, well, it's an orthonormal basis. W comma W doesn't, I mean, it's just one. Okay, it doesn't matter. V comma W, okay. So the projection of V on W is, I mean, the line span by W is V comma W, yes, this times W, very good. Okay, so that's the projection of this. So in particular, this is a projection of V on W1. Okay, now tell me, what are you going to do here? I mean, so you are, I mean, in this expression, what you wanted to give, you are constructing a projection of V on something. Now, is this formula correct?
No, it should be W.
Very good. It is Wk, right? But nevertheless, you see, you are projecting this. Then, well, at first you are assuming that the entire basis is given, because we have not defined what is Wn. We are defining now. Okay, so this element is missing. Therefore, the sum should run from where to where? N minus 1, right? And now you are projecting V on what? On each of these components of the orthogonal basis. Right. So now this sum resides where? On their span. On the span of this W1 to Wn minus 1. And what's that? That is this one, Wn minus 1. But we want to project it on the perp. How do we do? Yes. So how do you do that? Right. Okay. Yes. So this one is just defined as V minus this. Okay. All right. So that is actually what we are doing at each step. We can perhaps wipe this part out just to make it clear what we are doing. Okay. And not only for this case, for n minus 1, for every j intermediate values from 1 to n minus 1, we are just subtracting from V this, this scalars times Wk. We are projecting V on all the components of the orthogonal basis that we have got so far. Then we are taking the, we are taking just the sum of them, okay, subtracting it from V. And this one is the component of V in this, in this space, which is orthogonal to Wn minus 1. Okay. All right. So now you are just normalizing it, and you are getting Wn. Okay. Thus. Okay. So I hope the Gram-Schmidt orthogonalization is clear to all of you. If not, please let me know, or please write me an email and we can discuss. Okay.
Phi W and for B is 0.
Pi?
And phi W and for B is 0. We know that.
Yes.
That kind of gives us B in terms of.
Exactly. Yes. Perfect. Indeed. All right. So the orthogonalization is clear to you. If you are given some basis to orthonormalize with respect to some inner product, can you do that? You just have to do this, okay? At each step, not only for n-1, for every j, you do the same. Okay. And thus you obtain this one, normalize it, get the jth element of this basis. Okay. All right, Ayon, is it fine? Okay. So that's the end of today's class. In the next class, we'll see what we do, either spectral theorem or Sylvester's law. It depends on the time that we have. Thank you.